Welcome back to the course entitled Symmetry, Stereochemistry and Applications. We have just started discussing about the dynamic stereochemistry and aspects of stereoselectivity and stereospecificity. And in the last lecture, we have discussed a couple of examples and tried to understand what is called stereospecific and what are called stereoselective reactions. So we will continue our discussion in this direction with some more examples. Suppose if we have a cyclohexene and we try to do a bromination reaction, what we know for a bromination reaction is, when we have done in the previous class for the alkene, the bromonium ion could be broken from either side and formed two different compounds. But here, when we do the reaction in the same way, we only end up getting a compound which is the trans dibromocyclohexane and we don't get the corresponding cis dibromocyclohexane, because as we know, the reaction mechanism does not allow the formation of this cis isomer. No formation of this compound. Why is that so? If we try to understand using the formation of bromonium ion in the mechanistic path, the bromonium ion that may have formed in this reaction is this one. And then on this bromonium ion, if this Br minus comes from top, you would get a product where the Br will be up, the hydrogen will be down, and here the hydrogen will remain up and the bromo will go down, so it is trans. If the bromine attacks from the bottom here, then also you get the same product. If bromine attacks from the top on this carbon, what you would get is bromine up, hydrogen down, and in that case the bromine on this carbon will be down. So this is always, it forms the trans isomer. On the other hand, if we try to see what happens when you try to do an elimination reaction with a cis compound, which is this cis 1-bromo-2-methyl cyclohexane, the conformation of this molecule should be identified for an elimination reaction to happen. So if you do an elimination reaction on this compound using KOH in ethanol medium, OH minus will take away this proton. As a result, a double bond will form here and bromine will be eliminated. So we will end up getting a product which would be this one. Along with this, there is a possibility that the other product which can form from that particular proton also forms as a second alternative product. But if we had done the reaction with the corresponding trans isomer, which if we try to write down the corresponding chair form of this cyclohexane, the trans isomer will have the methyl in the anti position. So when you do the same reaction with OH minus, there is no hydrogen in the anti-periplanar orientation with respect to the bromine on the first carbon. So the elimination happens from the third carbon and you end up getting a product which is this one, the only product. This reaction is producing two different compounds, whereas this particular reaction is producing only one compound. So here it is the substrate specific reaction. So what we see here is substrate specificity, and in this particular case it is highly selective for this particular compound formation. So let us try to see the case of product selectivity. So here what does it mean is that you start with a substrate and perform a reaction with a given reagent. You get two products, 1 and product 2. And what you see is that the product 1 is a major product and product 2 is a minor or trace product. And these two products may be a pair of diastereomers or a pair of enantiomers. So when a diastereomeric product is preferred, then the reaction is called product diastereoselectivity. And when an enantiomeric product is preferred, then we call it as product enantioselectivity. Let us try to understand this with a couple of examples. Suppose we are doing a reaction with a terbutyl group present on a CC double bond, and we are doing a reaction with bromine in dichloromethane. So I will show you in the next slide that it forms two products. And these two products are a pair of enantiomers. But then one of these product will be in excess compared to the other. That means we will see that this reaction is enantioselective. But when we do the same reaction with bromine in water, we will again get two different products, that is product 3 and product 4, and we will see that these products are pair of diastereomers. And we will see a selectivity among these two products, so this reaction will be a diastereoselective reaction. So let us see how this reaction proceeds. As we all know that the addition of bromine in a CC double bond goes through a cyclic intermediate called the bromonium ion. The first step of this reaction is the formation of bromonium ion, as I am trying to show here. So now in this particular bromonium ion intermediate, what we see is that the Br minus that attacks has now a preference for this center, which is less crowded, the center 1, and the center 2 is more crowded because of bulky tertiary butyl group. So when the compound, when the Br minus attacks the first carbon, the product that we get is this one. And when the Br minus attacks the second carbon, the product we get is this one. And this is the major product, because bromine Br minus, when it attacks 1, it has more preference because of less hindrance in reacting. So this enantiomer gets preference over the other enantiomer. So the enantiomer 2 is the minor product. So here two enantiomers are formed, and these two enantiomers are formed in unequal amount. So we can term this as the enantioselective reaction. Now if we see the second reaction, where we are trying to treat the same alkene with bromine in water, what we know is that bromine in water forms the halohydrine, but that halohydrine formation also goes through the formation of bromonium ion to start with. So this bromonium ion is first formed, and then the water molecule has possibility of attacking the carbon center 1 or the possibility of attacking carbon center 2. So now again what we see is carbon center 1 is less sterically hindered. As a result, the product that will form by the attack of water on carbon center 1 is going to be the major product, and the one which attacks the carbon center 2 will be the minor product. So let us try to draw the two compounds that are going to form after elimination of H plus obviously in this particular reaction. So here the product 3 and 4 are a pair of diastereomers, and preferentially this product 3 forms as a major product, while this forms as a minor product, and hence what we see is this particular reaction is a diastereoselective reaction. Hope you can understand the difference between the enantioselectivity and diastereoselectivity from these two examples. Let us try to now see what is called the substrate selectivity. So in a substrate selective reaction, suppose you have two different stereoisomers, substrate 1 and substrate 2. You do a reaction, you get a product 1 which is coming from substrate 1, and the substrate 2 remains unreacted. So this reaction is called a substrate selective reaction, and this substrate selectivity or substrate selective reaction happens in case of enzyme catalyzed reactions. So now let us try to understand the principle of stereoselectivity. Principle of stereoselectivity means that stereoselective reactions are essentially stereo differentiation reaction where one of the two stereoisomer is differentiated by the reagent in a given chemical reaction. So there are in general 6 categories of stereo differentiation under 2 general classes which are called enantiodifferentiation and diastereodifferentiation. So let us see what are called enantioddifferentiation. Under enantioddifferentiation, there are 3 types of differentiation reactions. The first one is called the enantiotropic differentiation, where a chiral reagent or chiral agent, which can be a reagent, solvent or a catalyst, differentiates between 2 enantiotropic groups present in a molecule in a given reaction. So when the enantiotropic groups are differentiated by a chiral reagent, then we call it as an enantiotropic differentiation. The second type is called the enantiophase differentiation, where a chiral agent, a reagent, solvent or a catalyst differentiates between 2 enantiotropic phases. That means the phases of a double bond. It can be a CC double bond or a CO double bond. So when the chiral reagent differentiates between those 2 phases and gives you different products with different amounts, one of them being the major product, then it is called the enantiophase differentiation. The third type is the enantiomer differentiation. Here, a chiral reagent differentiates between the 2 enantiomers in the process, and this process is not necessarily a chemical reaction, as it includes chiral separation of pure enantiomers from their racemic mixture using a chiral column. So that chiral column has a chiral reagent which interacts with one of the 2 enantiomers and blocks the passage of that enantiomer and allows the passage of the other enantiomer through the column, and one can separate a mixture of enantiomers using this kind of column chromatography. The other type of differentiation is called the diastereodifferentiation. Diastereotropic differentiation means a chiral reagent, the solvent catalyst differentiates between 2 diastereotropic groups in such a reaction and produces one product in excess compared to the other. It's called the diastereotropic differentiation. Diastereophase differentiation is a case where a chiral reagent, a solvent or a catalyst differentiates between the 2 diastereotropic phases in a reaction and produces one diastereoisomer in excess. The last type of diastereomer differentiation happens when the diastereomers react at different rate as they have different internal energy. In principle, the rate of reaction is different when the product is common in both the reactions. So this is very important for you to understand. We will continue from here in the next class. Thank you.